We previously worked with random variables that are normally distributed. So we look at variables x and y, for example, normally distributed, but we look at them in separate contexts. We are going to look today of what happens if we put them together. So a bivariate distribution is formed by probability that a certain event will occur when there are two independent random variables in the scenario. The distribution, called bivariate distribution, will give us the probabilities of each possible choice of one element from x, one observation from the distribution x, and one observation from the distribution y. So the big question is, how do we decide that variables x and y are independent or not? In a previous section, we look at the correlation coefficient between two sets of data, how correlated they are, how strong is the correlation between them. But now we have whole populations, x and y. We cannot look at the entire population. Therefore, we are going to take a set of observed values. So a sample of size n will be x1, y1, where x1 is from the distribution x and y1 is from the distribution y, x2, y2, and so on up to xn, yn, where all xi are observed values from the variable x and y are observed values from the variable y. So we can look and find the sample product moment correlation coefficient, R, for this sample. Now, if I continue generating more and more samples, I would find more and more R's. And the question is, what would be the distribution of these R's, of this sample product moment correlation coefficient? So the proof is beyond our syllabus, but we can think of it in this way. Let R be the random variable of the sample product moment correlation coefficients. It has been noticed that if x and y have a bivariate normal distribution such that the product moment correlation coefficient is 0, then the sampling distribution of R, square root of n minus 2 over 1 minus R squared, is a t distribution with n minus 2 degrees of freedom. This tells me that in order to test a hypothesis of x, y being independent, so rho is 0, versus xy is not independent, I would be under H0, xy independent. So rho is 0, therefore I know that this variable follows this distribution. I'm going to take an observed value, calculate the sample product correlation coefficient, and this will be my test statistic, and I will see on this distribution how rare is this test statistic. If it is at the end of the tail, very, very end, depends on the significance level, then I will decide that I reject H0. If it's somewhere in the middle, I decide that I accept H0 if it's not a very rare event. The procedure is the same as before. Just remember what is your test statistic. What is your test statistic and what is the distribution of the test statistic. So we're going to take an example. As always, I'll take the easiest question and I'm going to leave you the next ones which are more difficult. Yes, I know, life is not fair. Okay, so let us look at this question. I put the data in my GDC. And with the GDC, one button, I go menu, stats, stat tests, linear regression t-test, option A. X list is called maths, Y list is called physics, line of regression, two-tail test, and that's what I have. Remember R. So R is 0.67169, and that's upper part. It was a long list. Okay, that's my T, the test statistic. T equals 2.564, 564, yeah. My test statistic is placed on the T distribution with 8 degrees of freedom, n minus 2, and in my case n equals 10. So whatever my distribution looks like, it's a two-tailed test, so I'm looking at this test statistic, where is it placed on this distribution? So if I'm at a 5% significance level, I'll look at 5% on that side, 2.5% on that side, and 2.5% on that side. So we can use inverse T with 8 degrees of freedom. So this one is a T distribution with 8 degrees of freedom. So I'm looking in my GDC at the inverse T here. So my distribution is symmetry by 0, very similar to the standardized normal distribution. And I'm looking at my test statistic. My test statistic is 2.56. So this is 1.8, the critical value 860. And my test statistic is 2.564. So it's in the rejection region. So at 5% significance level, reject H0. And of course, I should have started the question by stating H0. Rho equals 0, meaning that the two variables are not correlated, so x and y are independent, and h1 is rho is not 0, therefore x and y are correlated, and the variables x and y are not independent, are dependent. In this case, at 5% significance level, I reject h0, therefore x and y are not independent. To find what happened at 1%, I need to find the critical values for 1%. So I need on this side 0.5% and on the other side 0.5%. Now I learn, because my test statistic is right to the right is positive, I just look at the upper tail. And I get here the critical value for the upper tail. The critical value, I better draw a better diagram. For the upper tail, at 1% significance level, so area here is 0.5%, I get the critical value as being 3.36. Therefore, my test statistic 2.564 is here, so I accept H0. So at 1% significance level, I accept H0. At 5% significance level, I reject H0. And you express your conclusion in terms of x and y. Now, what can I do without GDC? Not too much, because the only thing I can do is to calculate the test statistic by hand. So remember that the test statistic, if you look at the previous page, the formula was r square root of n minus 2 over 1 minus r squared. So in my case, it was, we found r. So if you replace that r and n equals 10, let's see what we get. Surprise, exactly the 2.5644 and so on. So 2.564 to 3 significant figures. So exactly the value here. And my last advice is for you to look at the example 64 and the next questions in this exercise. So pause the movie and try the question by yourself. You might want to think deeper, because when the question and the text were devised before, schools had TI and SPIRE, which can do inverse T distribution. I think this solution is meant for the old types of GDC where it was not such a function as inverse T. So I'm sure you can find more efficient ways to solve this question. And with this being said, well done, guys, you completed the syllabus. Give yourself a big round of applause, though we know that some of you might look like that. We love you guys and we wish you all the best, Mr. Coventry and Mrs. V.